So welcome everyone to my YouTube channel. So today we will see the type 3 of the non-exact differential equations. So in the last video we have already discussed the first type and the second type of non-exact differential equations. So we saw that whenever we multiply the non-exact differential equations with an integrating factor, we convert them into exact differential equation. And once it is converted to exact differential equation, you can use this formula and easily find the solution. So let's begin with our today's discussion. So whenever you will get a differential equation of form m dx plus n dy, first you will check for the is it a exact differential equation or not. So once the dou m by dou y is not equal to dou n by dou x, it means that it is not exact differential. So we saw different types like type 1 and type 2, and today type 3, where we will see how to convert them into exact differential equation first. Here you will have two cases. So when dou m by dou y minus dou n by dou x divided by n is equal to fx, or the second case is dou n by dou x minus dou m by dou y divided by m is equal to gy. So in these two cases, you will see that in the first case you get an independent function of fx, and in the second case you got an independent function of gy. So if you get fx, then you will multiply by integrating factor e to the power of integration of fx with respect to dx, and when you get gy, then you will use the integrating factor as e to the power of integration of gy with respect to dy. So we will understand this better with an example. So these three problems we are going to discuss in today's class. So let's begin with our first problem. So this is m and this is our n. So always what we do, we first find dou m by dou y. So dou m by dou y will become, so m is yx plus y square, and we are partially differentiating with respect to y, so we will keep x as constant. You will get x because x is constant, and differentiation of y with respect to y will give you 1 plus 2y. And let's find out dou n by dou x. So dou n by dou x will give you, so n is x plus 2y minus 1. So now you will get 1 plus 0 plus 0, because again we are partially differentiating with respect to x, so y is constant and 1 is constant, so it will give you 0. So here you got 1. So here you can clearly see that dou m by dou y is not equal to dou n by dou x. So we will check for the two cases we have studied today. So if dou m by dou y minus dou n by dou x divided by n, you should get an independent function of fx. So you got x plus 2y minus 1 divided by our n is again x plus 2y minus 1. So you can clearly see that it will get cancelled and you will get 1. So 1 is also like a function of x only, because you can just think of this like x to the power 0. So once you get this case, so you will find integrating factor as e to the power of integration fx into dx, and our fx is 1, so e to the power of 1 into dx. So you will get ex as integrating factor. So what we will do, we will multiply this entire non-exact differential equation by the integrating factor, and it will give us a exact differential equation. So let's do it. So y into x plus y into x plus y into ex. So this is our m term will become this into dx, plus the second term will become x plus 2y minus 1, x plus 2y minus 1 into ex dy equal to 0. So this is now our exact differential equation. So we need not to check for the exactness now, because so this is like a algorithm that you have to keep in mind. So this is your m and this is your n. So if you don't believe, you can check for exactness, but it is an exact differential equation, because once you multiply by the integrating factor, you get exact differential equation. So what we do, our formula was, we keep y as constant and we integrate m dx plus n terms without x. We integrate with respect to dy plus c. So this is the solution that we usually apply for our exact differential equation. So applying this here, what we will see that we will get y constant here, y into x plus y into ex dx plus here you will see that there is no term of n that is independent of x. So here you will get 0 dy plus c equal to 0. So this is 0. So just we have to solve this part. So we will split it first. So if you split it, you get ex into y into x, and the second term is ex into y square, that we have to integrate assuming y is constant. So we will split it again. So if you integrate this term, you will see that y square will come outside and ex integration will be ex only, plus here you will see y will come outside and you will integrate ex into x dx plus c equal to 0. So now here we will apply integration by parts. So we know that integration by parts, whenever we integrate two function like function 1 and function 2, first we keep the function 1 outside and we integrate the second function minus, then we integrate the differentiation of first function and we multiply by the integration of the second function and we combinedly integrate them. So this is our integration by parts. So this video we are not going to see how we actually do this. It is expected that you should know this. So doing like further solving it, y square ex plus y. So here applying integration by parts, you will leave x as it is and you will integrate ex minus, then you will integrate, so you will differentiate the x. So on differentiating of x you will get 1 and you will keep this. So integration of ex is ex, then dx, so plus c equal to 0. So now next step will be y square ex plus y times of, you get here x into ex minus ex plus c equal to 0. So this is our final equation, final solution of our differential equation. So now let's move on to our next problem. So you can pause this video here and you can try this solution by yourself. So now let's start and try to solve this second problem. So if you see, this is our m and this is our n. So again we will find dou m by dou y as always. So dou m by dou y will be dou y, so it is y into log y. So we have to use our chain rule of differentiation. So first we will keep this as constant and we will differentiate log y. So you will get 1 by y plus, second we will differentiate y and we will keep log y as constant. So you will get 1 plus log y. Now finding dou n by dou x. So n is our x minus log y. So you will get 1 for the first term and this is constant because we are partially differentiating with respect to x. So y term will be constant. So you will get 0. So now if you see here, then dou m by dou y minus dou n by dou x divided by n. So always remember that whenever you are subtracting, n term is on the RHS side, it is being subtracted by the m term, then it should come in denominator. So this is a trick to remember this. So dou m by dou y minus dou n by dou x will give you 1 plus log y minus 1 divided by n is x minus log y. And you can see that it is not helping us. You will get log y by x minus log y. So it is not helping us. So we will do the other way. We will actually this time try to find dou n by dou x minus dou n by dou m by dou y minus m. Again the same trick. If m is being subtracted by the n term, that is dou n by dou x, so you will divide it in the denominator. So doing it, dou n by dou x is 1 minus, and dou m by dou y is 1 plus log y. So it will give you minus 1 minus log y by m is again if you see for m, y into log y, so you will get this 1 given and cancelled, minus log y divided by y into log y. So again you can see that log y will get cancelled by log y and you will get minus 1 by 1. So you can see again you have got a function of like gy. This is a gy function. It is independent of x. So in this type we have seen that the integrating factor we will find as integration of e to the power of gy, integrating this. So this is very simple to integrate. We will see e to the power of integrating our gy is minus 1 by y. Integrating with respect to dy, you will get e to the power of minus ln y. Now in the next step, we will take this minus 1 at the power of this y. So e to the power of ln 1 by y you will get. And finally, you will see that you will get 1 by y. So we are using simple log properties. So now you have to multiply 1 by y, this our integrating factor, to our this parent non-exact differential equation, to convert it into exact differential equation. So you can see that this y will get cancelled by this y. Okay, and here in denominator you will get a y, the second term. So let's rewrite it first. So log y into dx, log y into dx plus x minus log y, x minus log y divided by y into dy is equal to 0. So this is our exact form of m dx plus n dy. So this is m term and this is our n term. So we know we have to use this formula yc m dx plus n terms without x plus c equal to 0. So first our m term is log y. We will integrate with respect to dx assuming y as constant, plus the nth term without x is, so this term we will eliminate, only minus log y by y dy plus c equal to 0. So this part is very easy because this log y will come outside and inside you will get only 1 and it will give you x. So you will get log y into x minus log y by y dy plus c equal to 0. So only challenge is to solve this part. So it is very easy because you just have to assume log y is equal to t. Now differentiating both sides. So when you differentiate you will get 1 by y and dy is equal to dt. So just replace 1 by dy, like dy by y as dt. So here you will get, like you have to substitute over here. So you will get integration of log y, you have to write t, and dy by y will be dt. So we will get t square by 2 and our t is log y, so we will substitute it back. So log y square by 2. So our answer is, just rewrite is log y into x minus this second term that we have solved just now, log y square by 2 then plus c equal to 0. So this is our final equation. So I hope that you have enjoyed this solving this question. So this is the third question. So I would like you to try this question by your own because this video will turn longer. So, and if you are facing any problem, you can comment down and I can solve this for you. So that's it for today's class.